Hello, everybody. So, today we are going to talk about uncertainty in data. So, we will start with representation of uncertainty in data. So, there are three methods of representing uncertainty in data, like mentioned here: absolute or actual uncertainty, fractional uncertainty, and percentage uncertainty. Whenever we see data written something like this 2.2 plus minus zero point 0.1 milliampere. This is some current value in milliamperes. Whenever we see a data value written with some uncertainty like this particular form of uncertainty is known as absolute or actual uncertainty, like we have seen previously. Now, what do other forms of uncertainty mean? Fractional uncertainty and percentage uncertainty. So, if the average value of our data is represented, let's say, with a variable x, and the absolute uncertainty is represented with a variable delta x, in that case, fractional uncertainty is a ratio between the absolute uncertainty and the average data value, which in this case becomes zero point 0.1 divided by 2.2. We'll have to do the calculations. 0.045. Now, for absolute uncertainty, we always use the same unit as the unit of the quantity. For example, in this case, it will be milliamperes. But since fractional uncertainty is a ratio between similar units, it doesn't have a unit. Now, what is percentage uncertainty, or how do we calculate it? It's pretty simple. Fractional uncertainty, when taken as a percentage, which means multiplied by 100, gives you percentage uncertainty, which in this case will become 4.5%. Now, let's look at how do we calculate uncertainty in measured values. Now, what do we mean by measured values? Let's have a look. So, let's have a look at the three cases mentioned over here. When quantities are being added or subtracted, the actual or absolute uncertainty gets added. What do we mean by that? So let's just take as an example that we have measured a radius value of, let's say, a sphere to be 3.91 centimeter with an absolute uncertainty of 0.02 centimeter. Or I can just write it as, instead of repeating the unit twice, 3.91 plus minus zero point zero 0.02 centimeter. So this is the representation of the radius with the average value of the radius plus minus its absolute or actual uncertainty. Now, if I have to calculate the diameter of this particular sphere from the given radius, we know the method. Diameter is twice the radius, or in other words, radius plus radius. So when the two value of radii get added to give the diameter, what will happen to the uncertainty in the diameter itself? So since the radius gets added with itself to give you the diameter, which I can calculate here, so the average value of diameter will be 2 times the average value of the radius, or you just add them up twice, and the answer we get is 7.82 centimeter, 7.82 centimeter. What about the value of absolute uncertainty or uncertainty generally in diameter? That will be just a sum of the absolute uncertainty in the radius itself, which will be zero point zero 0.02 plus zero point zero 0.02, and hence it becomes 0.04 centimeter. So if I have to give the value of diameter, I have to write it down. I will write it down as d, the average value of diameter, plus minus its absolute uncertainty, which becomes equal to 7.82 plus minus zero point zero 0.04 centimeter. So now this is my diameter along with its absolute uncertainty, and you can see the radius uncertainty got multiplied by twice. Now, let's look at the second example, second case. When quantities are being multiplied, divided, the fractional uncertainty gets added. Now, what does that mean? Let's just assume we are doing an electricity practical where we measure PD and current. The PD value that we have is, let's assume, 2.91 volts. And since every measuring instrument adds some uncertainty to our measured values, there is the amount of uncertainty over here is, let's assume, 0.05 volts. So I will write down the average value of voltage or PD along with its absolute uncertainty, somewhat like this. Whereas the current value is 8.66 milliamperes with an absolute uncertainty of 0.03 milliampere. Currents usually that we work with in the lab are small currents in milliamperes usually. So these are my current and PD values. Let's assume we have to calculate resistance. And for that, we use our Ohm's law. And just to recall, Ohm's law is V equals IR, which means resistance is equals to PD over current. If I have to calculate resistance using these values of PD and current, the average value of resistance will become 2.91 divided by 8.66, which is in milliamperes. So I will just convert, because we know in formulas you must put in the standard units. I converted the milliamperes into amperes. The answer for the average value of resistance that I get is 0.336 into 10 to the power 3 ohms. And since we have a 10 to the power 3, we can rewrite it as 0.336 kilo ohms. All right, now this is the value of resistance, but since we know that the values of PD and current that have been used to calculate resistance had some uncertainty in themselves, which means that the resistance value must have some uncertainty too. This is not the absolute value. There has to be some uncertainty in there. Now, how do we find it? Unlike the previous case where we were just adding the two absolute uncertainties, when we are calculating a particular quantity by either multiplying or dividing two variables, we calculate fractional uncertainty rather than absolute uncertainty. And how do we calculate it? I'm simply going to add the fractional uncertainties in PD and current over here like this. Now, fractional uncertainty, as we previously saw, is the ratio between absolute uncertainty and the average value of the quantity. Absolute uncertainty in PD is zero point zero 0.05, and the average value of PD is 2.91. And similarly, absolute uncertainty in current is zero point zero 0.03. All values are mentioned right above. And the average value of current is 8.66. And by the way, current is in milliamperes in both cases. So I will just use the exponent 10 to the power minus 3. If I simplify this, I end up getting a fractional uncertainty for r, delta r over r, to be a value zero point zero 0.02. 0.02. That is the fractional uncertainty, which is delta R over R. Now, since we know when data is represented like voltage and current, when data is represented with uncertainty, we need to write down the average value of the data plus minus its absolute uncertainty. So we need to get the absolute uncertainty for R, which is pretty easy. Since delta R over R is zero point 0.2, just using cross multiplication, my delta R will be 0.02 multiplied by R, where R is the average value of resistance, which we just now calculated. So I'm just going to do the math over here. 0.02 multiplied by 0.336, which is kilo. Kilo means 10 to the power 3. I can keep it in kilo. I don't need to even use 10 to the power 3. I can just write the K to represent kilo. The answer, and since we are, by the way, measuring resistance average value in kilo ohms, its absolute uncertainty will also be calculated in kilo ohms, because as we saw previously, whatever is the value of the average, whatever is the unit of the average value of data, same should be the unit of its absolute uncertainty. If I do the multiplication here, I end up getting 0.007 into 10 to the power 3. Again, 10 to the power 3 is just representing kilo ohms, so I can write it as 0.007 kilo ohms, which becomes my absolute uncertainty in the value of R, absolute uncertainty, which is delta R. Now, we have to be careful about how many digits after the decimal place we choose here. My actual answer that I was getting when I was multiplying zero point zero 0.02 with r, my actual answer was 0.0068 into 10 to the power 3. But I did not take the whole thing. I just took the first three digits after the decimal point. Why am I doing so? There is a reason and I will explain. So now if I wish to write or represent the value of resistance along with its absolute uncertainty like we do for data, if you remember, we begin with x plus minus delta x, right? This is how we represent data with uncertainty. If I wish to write down the value of resistance with its absolute uncertainty, I will write down the average value of R, which I calculated over here in this step using R equals V by I. And that value was 0.336 with a unit of kilo ohms plus minus its absolute uncertainty, which must also be in kilo ohms, which is over here 0.007. So I will write it down 0.007, and I can just write kilo ohms once outside the bracket. So that becomes a representation of resistance with its absolute uncertainty. Now about the decimal places. So my average value of resistance was how many digits after the decimal point? 1, 2, and 3. If the average value of our data is up to three places after the decimal point, then my absolute uncertainty must not exceed three places after the decimal point. So it cannot be five or four places after the decimal point. But if my absolute uncertainty was coming out to be 0.07, then we could have just written it as 0.070 when representing it in as the absolute uncertainty of R. Hope that helps.